Awesome. Let's get started. So, my name is Luke. I'm part of the FreeFlyer development team. And today we're going to be looking at one of the new features that's going to be coming out in FreeFlyer 7.8. It's going to be called Optimal Control. So, let's get back into it. So, first, we're going to talk about how FreeFlyer solves trajectory problems today in the current iteration. And after that, we're going to talk about how FreeFlyer is going to solve those problems in the upcoming release. So originally, FreeFlyer optimization was released in 7.6. It was very generic optimization capability. It allows you to interface with three different optimizers. And the process by which you do that today is kind of a manual one. It requires a lot of user overhead in order to function. You can solve problems with it, but it takes a little bit more. It takes a little bit more manual management than you would have liked. So some of the features that we implementing in 7.8 are going to remedy that. So let's look at this problem right here, which is one of the sample mission plans that you can find in FreeFlyer today. It's called the Lunar Flyby sample mission plan, and you can find it in the optimization folder in FreeFlyer. But basically what this problem does is it walks you through solving and optimizing a flyby for Moon. And it does that using a couple of different segments, which you can see highlighted in different colors on the screen. So how this sample mission plan goes about solving the problem is you have individual variables at each of the patch points. So we'll look at this first patch point here. You've got variables for your position, your velocity, epic, mass, etc. You've got constraints for what your initial Keplerian elements are going to be. Moving on to the next patch point, we've got a similar set of variables. We've got constraints that are going to say, okay, we want to be continuous in position and velocity at this patch point between the segment behind and the segment in front of us. And we're going to do similar things at all three of the other patch points. And once you accumulate all of these variables, you have 50 or 60 in this problem and a similar number of constraints. And each one of those variables and constraints has to be individually managed by the user. Each constraint has to be individually calculated and assigned by the user. So what we are building now to be released in 7.8 to make some of this easier for the FreeFlyer user that wants to do optimization is we're building a segment object called a trajectory segment. Basically, this trajectory segment object is going to take all of those individually managed state variables and constraints that have to do with the actual trajectory and hiding them in the backend so that you as a user don't have to think about it. And there's a lot of advantages to doing that, and we'll get to what exactly those advantages are in just a second. But first, let me explain how the trajectory segment object works just a little bit. What you're looking at on the screen is a visualization of the information that's held inside of the object. We've got a discretized trajectory, which basically means there's a bunch of points that are going to represent the trajectory. You've got to use the trajectory segment object in combination with the optimizer in order to ensure that the segment is valid and the gravitational dynamics are being represented well. We're also adding a new ODE solver into FreeFlyer. Today, you use integration in order to solve your dynamics. Going forward, you'll be able to use something called collocation, which is a mathematical concept that you can use to solve ODEs. And I won't bore anybody with the math today, but it's a really interesting concept. So if you've never heard about it or read about it, it's worth a read. Now, once you have one segment, you can easily add a second or third or any number of segments and easily connect them to form a larger trajectory. So once I have my individual segments, in order to link them up, all I have to do is tell FreeFlyer, hey, I want you to link these segments in position, in velocity, epic, whatever it is, or all three. Let's say I want to have a delta V. I want to model impulsive delta V in between two segments. I can say just link in across position and epic and don't link across velocity. there's automatically a delta V due. So how do I solve a problem using this new approach? The first step is to generate an initial guess. So kind of how we were looking at like these segments here before. We take an initial state, propagate it out, and you form your initial set of discretized points for your segment that way. Take the segments, once you've generated the initial guesses, add them to the optimizer. Do that linking structure like we were talking about. You say, I want to link segment 1 to segment 2 to segment 3 and so on. Once you've done those 3 steps, all that's left is to solve. All you got to do is hand it to the optimizer and say go. So what we're looking at on the screen is an initial guess that we generated to a problem that basically goes from a Lyapunov gray body orbit and designed to transfer out to a halo orbit. So you can see we've got light blue segment, purple segment, dark blue segment, red segment, and then green segment. So we've got 5 segments in this problem. We're going to link each one of them. So the segment that connects to the initial Lyapunov orbit is that light blue one. And the following segment is the purple one. So we're going to link light blue to purple in position only. We want a delta V there in between those 2 segments. We do the same thing for purple, dark blue, and then again for dark blue to red. You can see that in the initial guess for the problem, there's a bit of a discontinuity in between those 2 segments. That's a problem that the optimizer is going to fix for us. And again, we need to link red segment to green segment. We're not going to model a delta V there. And of course, you need to tell FreeFlyer what kind of boundary constraints you want. So we want to make sure that we're connecting to that initial Lyapunov and ending up in that final halo orbit. So once you've done all this, hand it over to FreeFlyer. FreeFlyer will take a second to think about it. This is the solution that it spits out for that particular problem that we were just looking at. So this is the solution optimized. We've got 3 delta V's. So there's that first delta V. In case anyone's curious, the total delta V for this transfer, I think, was around 200 meters a second, maybe 210. So there's our third delta V heading out into red segment. We're going to do a couple flybys of the moon before heading back into cislunar space. Finally settling into that halo orbit. So this problem is just a little example to show some of the complexity that these new objects can take. Now, it didn't take long to set up this problem at all. I could have gone over the script in this presentation easily, but again, boring thing to look at. So we just looked at the ending solution. There's a couple of things that make these segment objects a lot better at solving trajectory problems than the current approach that you're using FreeFlyer. To start off with, all of the information is kind of condensed into the segment object architecture. So there's a lot less things that you have to look at on the screen when you're coding your problem, a lot less things to think about. And also, because of the side effect of that is the script is a lot smaller, so there's less things for you to type. In terms of actual problem-solving power, these objects are going to be able to solve more complex problems and be able to solve them faster. And that's because of two things primarily. The first is we've got the ability to provide analytic derivatives in the back end for all of the trajectory constraints, which today in FreeFlyer, all of those derivatives have to be finite difference. And the second thing is because the trajectory is represented via a discretized node structure, and that structure decreases the sensitivity that the optimizer has to deal with by a fair amount. So those 2 things greatly enhance the type of problems you can solve. And along those lines, so talking about sensitivity, that is, one of the other benefits of these objects is going to be your initial guess is going to be able to be a little bit more wild than it previously could have been. So we're going to look at a lunar flyby optimization problem to kind of look at an example of that. So what we're doing is we're saying we want flyby of the moon, and we want to maximize our orbital energy post flyby. So this is the initial guess that we're looking at. We're going around the front side of the moon. We're going to look at this, watch this video of the optimizer kind of thinking about the problem. You'll see that it actually takes a flyby and turns it all the way around the backside of the moon. So here's that initial guess overlaid with the final solution. And you can see we start out at that an energy level around negative 480. We end up around negative 420. But in order to find that higher energy level, the optimizer had to take that initial guess that we gave it and flip it all the way around to the backside of the moon and get it with no problem. So again, this is one of the benefits that you'll see using these trajectory segment objects, and it's a direct effect of the way that the trajectory is discretized into a set of points. So the last big thing that is included in these optimal control features is, of course, the actual optimal control part. So what we're looking at on the screen here is an optimized flyby of Earth, but we're not using impulsive delta V here. We're using a continuous thrust profile. So these little white lines coming off of the blue trajectory there are the instantaneous control directions that the optimizer has solved for at every point along the trajectory. So that red line is the ballistic trajectory. If we don't use any delta V, that's the trajectory we get. Once we feed the segment along with the the thrust profile into the optimizer, we tell it we want to optimize for maximum inclination change post flyby. And you see that the optimizer basically said in the first half of the trajectory, you want to direct your thrust downward, and somewhere in the middle of the trajectory, there's an inflection point. You want to flip and point your thruster up. And that's the optimal thrust profile for this problem. But the powerful thing about these continuous thrust profiles is, the optimizer it wasn't forced to say, there's going to be one thrust direction and there's going to be a second thrust direction. By using this continuous thrust profile and feeding it to the optimizer, I was allowing it to individually decide what each and every one of these little lines was supposed to be, in which direction it was supposed to be pointed at. So I can feed this same segment to a different problem and not have to think about what the actual structure of the thrust profile is going to look like. The optimizer will figure it out all on its own for me. So to recap, these new features are going to make solving trajectory problems in FreeFlyer faster. Things are going to be more performant. The optimizer is going to be a lot more convergent than it was previously, so it'll help you solve more complex problems. You'll be able to feed the optimizer worse initial guesses and still find a good solution to the problem. You'll have to write less script to do it, and of course, what we were just talking about, you can now use continuous thrust profiles in FreeFlyer. And those continuous thrust profiles, by the way, they'll enable a lot of low thrust analysis that previously couldn't be done in FreeFlyer. Although they're not restricted to that use case, you can, that thrust level is a user-defined property of the continuous thrust. And last but not least, we'll be doing beta testing for this feature. So if you'd like to be a part of that, you can use that QR code on the screen, just point your camera, your phone's camera at it, or you can send us an email at that address that's on the screen. Basically, what will happen is we'll send you a development build of FreeFlyer with all of these features packed into it. So it lets you have early access to the features before we release them, and it also allows you to have an influence on what the final design looks like. So you can help us tailor these features to your use cases. And it also helps us find a lot of bugs in software that we would typically find after release, and we can fix those beforehand. So good for everybody. And that's all I have. Mark, back to you for questions.
Cool. Yeah, thanks so much, Luke. We do have a couple questions. I'll start off with one question that says, once these segments are released, will there be any reason to use the generic optimization capability, or should you always use these new features?
Well, the segments are going to, again, they're trajectory specific. So there are a lot of constraints that you might want to apply to a problem that aren't strictly dynamic in nature. So let's say I want to have a ground. I want to make sure I have ground station contact at the endpoint of my segment or something like that. I would use the generic optimization capabilities that are already in FreeFlyer in order to do that in conjunction with the trajectory segment. So this doesn't necessarily make the current features obsolete. It just upgrades in the whole.
Okay, great. And kind of following up on that, would you use this to design low thrust LEO to GEO transfers or GTO to GEO transfers?
Yes. That would be a great use case for these new segments.
Another one we have, the visualizations that you were showing for the thrust profiles and the segments, what kind of visualization mechanisms were you using to create those visuals in FreeFlyer?
Well, at the moment, they were produced using graphic overlays. We're still working on packing all those visualizations into the back end. So yeah, right now, for all of these, all the material you saw today, all of those visualizations were produced via either graphic overlays or just using the regular spacecraft tail mechanics that are already included.
Okay, and then another question. Would you recommend using the targeter to get seed values, or do the new enhancements allow for worse initial guesses?
Using the targeter to find an initial solution is definitely a valid approach. It's not something you have to do. You can generate an initial guess and feed it right to the optimizer without doing any targeting. It's really up to you as a user which way you want to go about
it. Okay. The next one we have is, were you doing the optimization shown in the reduced dynamics of the CR3BP, or was it in a full ephemeris model?
The Lyapunov, the halo transfer was CR3BP. So we just had the only gravitational sources of the Earth and Moon there, and the Earth was in an ideal circular.
Okay, and then I think, let's see, the last one was, can the trajectory segment be used to design planetary tours or asteroid tours?
Yes. Yeah, pretty easy. That's actually one of the test cases that we're using to validate the features as we're building them. You take one segment. At the end of that segment, place a constraint that says I want to be close to this asteroid or this planetary body to ensure we're doing a flyby. Take a second segment and just link it up to the back end of that first one. There's your flyby, and that's actually the method that was used to do the lunar flyby energy maximization example that was a few slides back.